in presenter mode? That's perfect. Thank you.
Okay, perfect, perfect. Okay, well, thanks to the organizers for inviting me to present in this workshop. So I am going to be the first of a few talks on the 0-pi qubit. And since I'm the first, I will give a little bit of an overview of this solid state implementation of a protected qubit. And then I'll talk about some experimental progress towards realizing the 0-pi qubit coming from my group at University of Wisconsin and the Plourde group at Syracuse. And this is work that has very strong theoretical support from Lev, who, of course, is now at Google. So here's an outline for the talk, and I'll begin with just a brief discussion of what we mean when we say protection. And as Michel was saying, I think a protected qubit, the critical thing is that you are able to suppress all errors, not just one class of error. And I will, just kind of present the criteria for achieving full protection generically. And then I'll focus on this 0-pi implementation. And then in the second part of the talk, I'll describe our experimental progress towards realizing the 0-pi qubit. The key piece that we need is an effective pi periodic Josephson element. I'll tell you that this is pretty straightforward to realize. We now have these robust pi elements. And in the last bit, I'll talk about some progress towards implementing protected qubits using these pi elements. Okay, what do we mean by protection? Well, the key thing we need to do is to achieve suppression of both types of error, both bit flip and phase flip errors. We want to have exponential insensitivity to these types of errors. And so what do we mean by exponential insensitivity? Well, one example that we're, of course, all familiar with is the transmine qubit. Now here you take as the starting point a conventional charge qubit with EJ over EC of order 1. And then if you increase the value of the shunt capacitance, so increase EJ over EC, then the wave function becomes highly delocalized in charge space so that the device becomes exponentially insensitive to fluctuations of the offset charge on the island. So you end up with a charge dispersion that is exponentially suppressed in this ratio EJ over EC. So this device achieves exponential protection against low frequency charge noise and dephasing from low frequency charge noise. But there's no protection against bit flips or dissipation with this type of device. So the transmon, I would say, is half protected, but it doesn't achieve full protection. But I'll show you that there is a class of qubits based on pi elements that in principle should allow us to achieve complete protection, exponential insensitivity to both phase flips and bit flips. Of course, for the qubit to be at all useful, you need to be able to do robust fault-tolerant logical operations. You need to have access to fault-tolerant single qubit Clifford gates and entangling gates. And so these are really the criteria for a fully protected qubit. Of course, it's desirable to have access to an additional non-Clifford operation in order to achieve, it's essential to have access to a non-Clifford operation in order to achieve universal quantum computing. And we would like for that non-Clifford gate to be robust, although as far as we know now, it's not possible to achieve a fully protected non-Clifford operation. So the 0-pi does provide access to this robust non-Clifford operation, but I'm not going to say anything about that in this presentation. Okay, so let's talk about the specific 0-pi implementation. So this was a qubit that was proposed by these authors here in the early 2000s, and the key ingredient is a pi periodic Josephson element. And the nice thing is you can implement such a pi junction using conventional materials, conventional aluminum oxide Josephson junctions. You can make kind of a metamaterial, Josephson metamaterial that will implement this effective pi periodic element. And if you take such a pi element and you shunt it with a large capacitance, then in the phase basis, you end up with this type of potential energy landscape with local minima at phase of 0 and pi. And the two lowest energy states are near degenerate, and they represent symmetric and anti-symmetric superpositions of wave functions that are localized in the 0 valley and the pi valley. Now, if you look at these wave functions in the charge basis, you'll see that they represent superpositions of large numbers of Cooper pairs, either even parity states or odd parity states. The wave function has an envelope that's very large in charge space, given by the ratio of E2, the second harmonic of the Josephson energy, to the charging energy. And the wave functions then are strongly delocalized, but for the ground and excited state, the wave functions are intertwined. And those are the two kind of critical ingredients for achieving protection. You need to have very strongly delocalized wave functions, but also wave functions for the logical states that are kind of intertwined in this way, so that from the standpoint of environmental fluctuations, these wave functions look almost identical. And this approach allows one to achieve protection. And
we have a question from Daniel. Do you mind, Daniel, if you can unmute yourself and ask?
Hi, Robert. It's Daniel. This is going to sound like a really elementary question, but I just want to really make sure I understand this. Is the black curve on the left plot a plot of the junction internal energy versus phase?
That's right. It's the plot of the energy landscape of the pi qubit, versus phase.
But it's just the junction energy, right?
Of the pi periodic element, correct.
Okay, so if you had a transmon circuit, so just a junction with some capacitance, then that would show the potential energy, and I could imagine that the capacitance sets some mass and it just lives in that potential.
Correct. Yeah, okay. But the critical thing though is here you know the phase is 2 pi periodic, and here you have these two local minima for your pi, right?
Yeah. Okay. Thank you.
Okay. Good. And as Lev was mentioning at the end of Michel's talk, there is a close connection between these types of strongly delocalized states where you encode in charge parity and the grid states of GKP. So as I'll show, this type of qubit, if we can realize it, will provide simultaneous protection against both bit flip and phase flip errors, access to fault-tolerant Cliffords, and although I won't discuss it, we do have access to a robust, unprotected, non-Clifford operation. So this idea has been around, as I say, since the early 2000s, and the initial proposals for implementing this type of qubit described, for example, in this paper from Brooks, Katai Preskill, they look great on paper, but when you look at the parameters that you would need to implement such a device, as an experimenter, you see that this is going to be exceedingly difficult, because this initial proposal for a frustrated plaquette of this form required extremely low Isabel for these superinductors, very large cross capacitance here, and experimentally very difficult to achieve the large cross capacitance that you need, and simultaneously have very small junction capacitances for the junctions in this plaquette. So, the parameter range that you would need to access to implement this type of device, it's really difficult. I think later on in this session, we'll hear about some very recent nice experimental progress towards trying to implement exactly this type of circuit. But it's hard. Technically, it's hard. Another issue is that for the sort of target values of EL that you need, you end up with any modest amount of disorder in the system with some very low-lying harmonic modes that will couple to the logical states, and that can give rise to some problems. And this is described very nicely in this recent paper from the group of Jens Koch. So, this looks kind of hard. So is there another way that we can try to implement this effective pi element? So one approach is to, not try to implement a robust, perfect pi element right out of the gate, but to work with imperfect pi elements that, although they have some, significant, first harmonic of the Josephson energy, they're not perfect. At least we can realize these in a clean room. If we can do that, then one path to protection is just to brute force concatenate a number of these imperfect elements. And so this is the approach that we're taking here, where the plaquette is this simple squid loop involving two conventional Josephson junctions and inductors that are not in the microhenry range, but only in the nanohenry range. So this is realizable. We bias each of these plaquettes at frustration. They become pretty good but imperfect pi elements. And then in order to make the composite element better and better, we just concatenate more of these imperfect elements. And so that's the strategy that we're taking here. And, I want to cite some prior work from Misha Gershenson and his group at Rutgers. I think what we're doing here differs from that in the key way that for the implementation that Wisconsin and Syracuse are taking, now we've got some local biasing of fluxes and charge on the entire array. So that's our strategy here. So let's talk about how such a circuit can achieve simultaneous protection against both phase flips and bit flips. So phase flips for these logical states are going to correspond to bit flips in the 0 pi basis. And so that means we're talking about tunneling events between the 0 and pi wells of this pi periodic potential. Well, we know very well how to suppress that type of error. All we need to do is to take the device and shunt it with a very large capacitance so that we achieve a very large ratio E2 over EC, the second harmonic of the Josephson energy to the charging energy of this shunt capacitance. And so that's going to give us an exponential suppression of these tunneling events between the local minima of the 0 pi valleys that will translate into a exponential suppression of phase errors in the 0 pi qubit. Okay, so that's easy to understand. How about bit flip errors? Well, bit flip errors in this logical 0-1 basis are going to correspond to phase errors in the 0 pi basis. Now, if we had a perfect pi element, the 0 valley and the pi valley would be exactly at the same energy, and there would be no mechanism for phase noise in the 0 pi basis. So in order to understand what these errors are going to be due to physically, we have to think about the internal construction of our pi element. And so, physically, these errors are going to be due to imperfections in the pi element, or in other words, to flux noise. In order to implement the pi element, we're taking these little squid plaquettes, and we need to frustrate every single plaquette. And if we're biased away from frustration, then we haven't fully suppressed the first harmonic of the Josephson energy. And that's going to give us a little bit of a mismatch in the 0 pi values that will lead to noise. Okay, so how do we deal with this? Well, the series concatenation here is going to provide the exponential protection that we need. Okay, so in the case of a single plaquette, we have no protection at all. We get this hyperbolic set of energy bands, and in the case of a vanishingly small tunneling rate, we just have a linear flux dispersion that gives us no protection. But as soon as we start to concatenate elements, then we begin to exponentially suppress the sensitivity of the qubit to flux noise. And that is the exponential suppression of bit flip errors in this type of device. So in principle, we can have both suppression of bit flips and phase flips. Let's talk a little bit about control. So with this type of qubit, the control is going to rely on modulation of capacitive and inductive shunt elements that will allow us to perform rotations in both charge space and in phase space to implement protected X and Z rotations. Okay, so how does this look? Let's talk about the protected Z gate first. So we take our plaquette, which is connected to ground with this very large shunt capacitance, and we put in series with it a squid switch that's normally closed, so that we've got very strongly delocalized wave functions in charge space, and the charging energy is quite small. If we then start to open up this squid switch, then in the charge basis, we've got some charging energy that we're modulating, and that's going to force these different components of the charge wave function to accumulate phase at different rates. And if we time the gate properly, then we can realize a gate where the ground state accumulates no net phase, but this logical one state that has this odd superposition, the number of Cooper pairs, is going to accumulate a 90-degree phase shift relative to the ground state. And so this is our logical Z operation. And you can imagine that if you've got some mismatch in the timing of your gate away from this matching condition, then you'll see that the wave function for your red logical one state, it's going to be not quite perfect, but it's going to still have exponentially small overlap with the zero state. And so errors in the computational subspace are going to be exponentially suppressed. And so this is going to be a robust fault-tolerant gate. In the case of the X gate, we're basically doing the same thing here, but now what we do is we take our plaquette and we connect it to a very large superinductance via a squid switch that is normally open. And it's easiest to think about this gate not in the basis of charge, but in the 0 pi basis, where we have states that are localized in the 0 well and in the pi well. As we connect this plaquette to the superinductance, then we're going to destroy the periodicity in phase. We're going to introduce an overall parabolic shape to this energy landscape in the phase basis, so that the wells at 0, 2 pi, 4 pi are no longer equivalent. And when we do that, that causes the different components in this grid state of even and odd parities to accumulate phase at different rates, just as in the case of the protected Z gate. And this type of operation will achieve a protected X gate. So this type of qubit provides access to protected X and Z operations using these capacitive and inductive shunts. In the interest of time, I won't say anything about the plan to do a protected entangling gate, but it also relies on these superinductive elements that are connecting qubits via a squid switch that is normally open. And so this qubit then allows access to the full fault-tolerant Clifford algebra. Okay, so let's switch gears a little bit and talk about implementation of this type of qubit. The key thing is a plaquette that involves Josephson energy, inductive energy, and charging energy of the junction that are roughly matched. We can implement this type of plaquette using either kinetic inductors for these inductive elements within the plaquette, or we can use Josephson junction arrays, small arrays involving about 10 junctions or so. And the energy scales are set by the charging energy of these smallest junctions. For us, it's comfortable to target energies of about 2 Kelvin. This corresponds to a couple of femtofarad for these small junctions. So, roughly 200 nanometer by 200 nanometer junctions, or 150 nanometer by 200 nanometer junctions. This is compatible with the same type of junction fab that is typically used for transmon qubits and other types of superconducting qubits. And note that the inductors that we need here are, they're large but quite realizable using 10 junctions or kinetic inductors involving 100 or so squares without great demands on the inductance per square of the kinetic inductor material. Okay, so the groups at Syracuse and Wisconsin have both implemented this type of pi periodic element. In order to characterize the devices, we embed the plaquettes in an RF squid loop that we read out dispersively. As we, and here's a picture of one of the devices fabricated at Syracuse using kinetic inductors for the inductors of the plaquette element. As we vary the flux bias through the plaquette loop, we see that we can transition between a regime where we have 2 pi periodicity in the plaquette and pi periodicity when we frustrate this little plaquette loop. And we're sweeping these biases to the RF squid loop and the plaquette bias, reading out dispersively. When we look at these 1D cuts, we can do some analysis, and we see that with this implementation, we are achieving a ratio of E1, the first harmonic of the Josephson energy, to E2, the second harmonic, which is the pi periodic harmonic. We achieve a ratio E1 over E2 of about 0.02. So it's clearly not perfect, but it's good enough for us to want to take this element and attempt to implement first pass at this protected qubit. So I'll talk in the remaining time about progress towards implementing protected qubits. At Syracuse, the team there has been working with a 2 plaquette circuit that involves 2 of these pi elements with local flux biasing on each squid loop, a local charge gate on the intermediate island, and charge gating on the qubit island here. And we shunt this 2 plaquette structure to ground with a large capacitance, similar to what's used for transmon circuits. So here's how the devices look. In this case, the plaquettes are implemented using a junction chain inductor. We've got one plaquette here connected to ground, another plaquette up here. The shunt capacitance is off this image over here. We've got local charge gating and local flux biasing to each of these plaquettes. So
we have a question from Matthew. Matthew, do you mind if you could unmute yourself and ask?
I mean, it could wait until the end. This is, I just had a question about the sensitivity of the gates. You mentioned that they're exponentially suppressed in errors, but how sensitive are they to timing variations or things like finite pulse rise time? But we can discuss that at the end if it's better.
Okay, yeah, I can maybe say a little bit about that at the end. Thank you. Okay, so to read out this qubit, we are using a CQED dispersive readout. We've got capacitive coupling to a resonator, and we can do resonator spectroscopy as we sweep the flux biases of the device. And we see that, we're nicely orthogonalizing the fluxes to these two plaquettes. We can easily identify the point at which both plaquettes are unfrustrated. One plaquette is frustrated, the other is unfrustrated, and we can identify the double frustration points where we expect to start to see some protection. So we can operate these devices as kind of conventional microwave modes, driving the plasmon transitions in one of the local wells of the energy landscape, and we get coherence times that are approach 10 microseconds or so. So they're, not great by state-of-the-art superconducting qubit standards, but they're not awful. But of course, what we really want to do is to be able to bias towards frustration and look at the evolution of the system in this a space that's spanned by wave functions localized in the 0, pi, and pi wells. So we prepare a state in the 0 left well, the ground plasmon state of this left well. We non-adiabatically bias to frustration. And what we would like to see is evolution in this subspace of the 0 and pi well. So this is the experiment that we're doing here. And in this case, Britton's group is approaching frustration from the left. As they near and get to frustration, you're seeing that there is a transfer population between the 0 well and the pi well that we can map out nicely. And the key experiment then for us to do next is to look for coherent dynamics in that subspace. Now, let me digress a little bit and say a few words about the sensitivity of this type of qubit to charge. Now, if you look at the energy bands corresponding to the 0 and 1 state as a function of the offset charge on this pi element, you'll see that you get these energy bands that oscillate sinusoidally with a periodicity 4e for each of the bands. And so you've got a tunnel splitting between the 0 and pi wells that's got an absolute value that is 2e periodic. So we would like to be able to stabilize the offset charge on that island, for example, at 0 charge, and operate at a place where the tunnel splitting is greatest. But in general, we don't have exquisite control over the offset charge on the island, and there might be some noise in that charge that takes us to another point where the tunnel splitting is smaller. And in fact, at offset charge of 1e, we get a gap that closes completely. So if we don't control the offset charge, we're going to have some charge noise that is going to decohere this qubit biased at this point of frustration. Now, things are even a little bit more complicated than that, because in addition to fluctuations of the offset charge, we can have fast quasi-particle poisoning that would switch the offset charge by 1e, presumably on quite fast timescales. And that is going to then give a tunnel splitting that's effectively e-periodic if this quasi-particle poisoning is quite fast. On the other hand, I want to point out that if we're biased at half e points, there are some quasi-particle sweet spots where poisoning would, let's say, take us between these two points in this energy diagram, or between these 2 points, that would preserve the magnitude of the tunnel splitting between our 0 and pi states. So in principle, we think even in the presence of quasi-particle poisoning, provided that random fluctuations of offset charge are slow enough, we think that at those sweet spots in quasi-particle, with respect to quasi-particles, we should be able to observe some coherent dynamics. So that's what we're trying to do here. And here's a first pass of this experiment where the Syracuse group is idling at a fixed time at frustration, single frustration in this case, and varying the offset charge on this plaquette element. We see some nice, clear periodic modulation of the population in the right well as a function of this applied gate charge. But unfortunately, when we fix gate charge and look for oscillations in time, so far we have not yet observed those oscillations. But that is our goal in the coming weeks to do that. I will say that the Syracuse group has also done some experiments where they've frustrated both plaquettes and shown that they have good control over the charges both on this intermediate island and on this qubit island. And we see that this charge configuration can be stable on sort of 10 minutes, couple tens of minutes time scale. And I think as an aside, there was some talk yesterday about these bursts in the context of high impedance resonators and other types of qubits. I think one development is that we really are starting to develop a pretty good quantitative understanding of offset charge noise. And, for one, I am personally not as afraid of charge noise as I used to be. This is some data from my group where we've simultaneously monitored offset charge fluctuations on 4 qubits simultaneously on a single chip. And a surprising recent result is that we see that fluctuations in offset charge are correlated over long length scales. Well, I think we can explain this now. So this is very intimately related to the burst physics we were talking about yesterday. My group has kind of mapped out the charge footprint of these burst events. And we've gotten to the point where we can make some pretty firm quantitative statements about the number of discrete charges involved. And we can even say something about a very small but measurable charge imbalance between positive and negative charges released during these burst events. So these events give correlated errors on long length scales. I think is something as a community we're going to need to deal with. But now that we're starting to understand the physics, I think that there's a path to mitigating this type of noise, this type of error. So in the remaining few minutes, I'll say a little bit about some experiments that we've done at Wisconsin. Here we're working with a slightly different circuit that just has a single plaquette element, but we do have this tunable capacitive shunt that's connected through a squid switch that we can modulate. So this is how the device looks. Again, we're implementing the plaquette using a junction chain for the inductance. And okay, we can operate this as a microwave mode, and we have coherence times of order microseconds. But of course, the critical experiment for us is to bias to frustration and look for the dynamics of the qubit in this 0 pi subspace. So when we perform, just as an aside, we can also look at the interwell relaxation. So we can prepare in, let's say, this right well and look for a slow relaxation over the left well. And the system will relax over very, very long time scales, well in excess of a millisecond. So that type of protection against dissipation, that's one of the ingredients for a protected qubit. But of course, it's by no means all that we need, but certainly we get that protection by having these wave functions that are well localized in the left and right wells. So when we perform this type of experiment where we prepare in one of the local minima, bias to frustration, and look for coherent dynamics, as in the case of the Syracuse experiments, we see a very clear modulation of the populations with respect to applied gate charge. So this looks very encouraging. But in this experiment, we're fixing the idle time and stepping through charge bias. When we do the experiment the other way around, where we set the charge bias on the plaquette and sweep time, so far we do not yet see evidence for coherent oscillations. So this is really the key ingredient that we need to demonstrate in order to move forward. If we can stabilize the charge and see some evidence of coherence with the single plaquette, then that is extremely encouraging, because then we can build from there. And this single plaquette that we're working with, I want to emphasize, it is a completely unprotected device. So why could it be that we're not yet seeing these coherent oscillations? Well, the usual candidates are noise and offset charge, quasi-particle poisoning. As I've described here, I think that the fluctuations in offset charge we understand. I think they're going to be slow enough that they're not going to be an issue for us. I don't think that's what's limiting us now. For quasi-particle poisoning, even if that's very fast, there are these quasi-particle sweet spots that we should be able to access that will allow us to observe coherence. I believe that the main culprit that we're going to have to worry about is flux noise in this plaquette. With a single plaquette, we have no protection. Given the flux dispersion of this device, we expect to get coherence times of order microsecond for reasonable values of flux noise. So this is not great, but it should be measurable. And if we can measure that, well, one plaquette gives us no protection, but then, it's going to be straightforward for us to go ahead and concatenate and then really start to see some of this exponential suppression of sensitivity to flux noise. So that's our program for the medium term. But I think we really need to understand the dynamics at frustration with the single plaquette element before we move forward and try to implement these more complicated circuits. So that's the end of my talk. I've given a little bit of an introduction to the zero pi qubit. I think it's a very interesting proposal for a solid state qubit that provides a full protection, simultaneously protects against both bit flips and phase flips. We've demonstrated the robust pi elements, so that's working well. And for the rest, we've got our work cut out for us. But if we can demonstrate some protection using these small numbers of plaquettes or some coherence, then there is really no ceiling, and definitely a path towards improving the device exponentially by series concatenation. So that's the program. And finally, I just want to put up this one slide. Our postdoc, Andre Klotz, has developed some nice code that we've described in the past at QCPR meetings. People have expressed interest. This code is now available on GitHub for those who are interested. Okay.
All right, we got quite a few questions. So if everybody doesn't mind biting into some of our break time, Matthew, why don't we start with Matthew's question first?
Yeah, again, my question was just about the protected single qubit gates and how sensitive they are to timing variation and control pulse non-idealities like finite rise time.
Yeah, I mean, if I can quickly go back here, I mean, you can imagine that you've got some imperfection in this Z gate. Well, then in this this space of the wave function psi real imaginary, you're going to have these little vectors for the different charge components that aren't quite pointing in the right direction. But you can see if you've got you're still going to have negligible overlap between that state and your logical zero. So within the qubit subspace, you're going to have exponentially small error. The only error that you have would be due to imperfection in your pi element, but you can make that in principle exponentially small. So the errors that you're going to get are going to take you out of the computational subspace, but those in principle are going to be easy to identify, and we can correct and bring the system back into the computational subspace. So, this approach to doing protected gates, it's this idea that's presented in this somewhat old now paper by Brooks, Kataya Preskill. It is exactly the same idea.
All right, great. Alexander, do you mind asking a question?
Sure. Do you hear me now?
Yes.
So I wanted just to understand, when you concatenate or make a chain of these pi elements, is it now the potential, the phase drop over the whole chain, which is 0 or pi, or in each element 0 and pi? And then the charge states, I mean, this even in all charges, now you have many islands. So on which island is this charge?
Yes. So we are going to want to bias the intermediate islands at 0 charge, and the phase drop that we care about is the phase drop on the chain. But if you've got 0 pi phase drops on the individual pi elements, then the phase drop on the whole chain is basically set by the parity of the phase drops across the individual elements. But if you concatenate a bunch of 0 pi elements, then you end up in the end of the day with a 0 pi element. And what you do by concatenating is you suppress the ratio of the first harmonic of the Josephson energy to the second harmonic.
So essentially it's a phase over the whole chain.
Correct.
Thank you.
All right, Ian.
Hi, Robert. This is Johan Pop. Can you hear me? Yep.
Yes.
So I'm wondering if you could say a few words about the physical mechanism that could lead to correlated charge noise on an insulating substrate at low temperatures.
Yeah. So it's exactly the same physics that you guys have been studying, and we're writing a paper on this right now. There are these burst events that we believe are due to absorption either of cosmic ray muons or gammas from low-level radioactivity in the laboratory. Now, those events are going to release hundreds of keV of energy, and most of that energy at the end of the day is going to go into a phonon reservoir. You're going to have high-energy phonons that are going to scatter down to the gap edge of the superconducting ground plane, and those phonons will break pairs and generate quasi-particle poisoning. But the other thing that happens is you're going to generate a lot of charge. For a silicon substrate, you get about 10 to the 5 discrete charges released in one of these charge bursts. Now, of course, a lot of that charge is going to recombine very quickly, but not all of the charge is going to recombine. And so you get some kind of stray charges that diffuse away from the impact site, and they're going to trap. And the footprint of this charge event is very, very large. And so that's what we see when we monitor simultaneously charge noise on a bunch of qubits. We see correlations on quite long length scales. And in order to monitor this physics, of course, we're working with qubits that are charge sensitive. You might say, oh, well, if we've got a transmon, who cares about this because we're insensitive to charge? But the fact is that the transmon is extremely sensitive to charge impulses, just as sensitive as a conventional charge qubit. And so these charge bursts basically just give you random rotations of the individual qubits that are all happening simultaneously. So this is an important correlated error mechanism. On top of this, there's the high energy phonons and the quasi-particle piece of this, but you also have to worry about the direct charging event from these bursts.
I see, but then I wouldn't expect the phonons to differ, significantly if I go from a sapphire substrate to a silicon substrate. But I would expect the charge burst to be very different in silicon compared to sapphire, because the band gap in sapphire is higher. Right. Is that correct?
We haven't done the experiments, but I believe that is correct. I believe that is correct. And we see some the qubit in some sense is a really lousy electrometer because you're only measuring charge modulo 1e. But if you look at the details of the charge histograms, you can actually say quite a lot about the physics of these charge events. And we even see a little bit of charge imbalance that we believe we understand as a consequence of the valley physics in silicon.
Oh, wow. Okay. Very interesting. Thanks.
All right. Sorry. We will, John, Oren, we'll have to take your questions a little bit later, possibly during the break, because I want to make sure there's enough time for the break. So, Andrew, do you mind if you can